So we had done some work with simplifying radicals, and if you remember, we talked about when we do this, it's best to find the largest perfect square factor of that radical. So that's just one additional step to simplify. So if we're talking about finding the square root of 80, we look at our perfect squares list to see where 80 falls. And 80 falls between 81 and 64. So we're going to start with 64 and see if that's a factor of 80, and we work our way back down to 1 to find the largest perfect square factor. Well, for us, 80 has a perfect square factor of 16, and it's 16 times 5. Since 16 is the perfect square factor, remember, think of this as the area of the square is 16. What's the side length? The side length is 4. So our simplified answer would be 4 square roots of 5. Now, if we look at our next one, we've got the square root of negative 64. We're going to take the same approach. We said, well, is there a way that we can make the square root of negative 64 look somewhat like the square root of 80? And we came up with a way of rewriting it so it was the square root of 64 times the square root of negative 1. We would look then at that square of 64 and say, is that a perfect square, or does it have any perfect square factors? Again, you can go back to your table if you want and look. 64 is a perfect square. So again, if that's the area of the square, what's the side length? That would be 8. Now, we also discovered that the square root of negative 1 is a special meaning of mathematics. That is the value represented by I. It's getting into your imaginary number plane. Remember, your imaginary numbers are built off of your real number plane. So again, your real numbers are your inputs, your imaginaries are your outputs. And so we could plot this just like we have with our other values on our real axis, except think of the imaginary as like your y-axis. And so you're not going left or right any on the real numbers, you're just going up to where 8i would be. And that was reviewed in one of your previous videos. So we've got one more problem to take a look at. And we've got the square root of negative 99. Again, we want to make it look like our first problem, the square root of 80. So we can rewrite that as the square root of 99 times the square root of negative 1. Focus on that square root of 99. Go to your perfect squares list. Remember, 99 is going to fall here. Work your way back to find the largest perfect square factor. For us, that would be 9. 9 times 11 is your 90. So if 9 is our perfect square factor, again, what's its value for the square root of 9? If the area of the square is 9, what's its side length? That would be 3. 11, not a perfect square nor a perfect square factor, so we leave it as is underneath the radical, and we do remember that the square root of negative 1 is represented by I. So our simplified result, remember, we want to rewrite our values on the exterior of the radical in front of the radical so we can keep those straight versus what's inside radicals and what's not. So we would prefer to write this as 3i square roots of 11. Simplifying radicals is foundational skills, especially when it comes to solving different types of equations, in particular your quadratic equations. And so here we have a quadratic equation. We've got a squared minus 49 equals 0. How can we solve this? Well, we can see that we're subtracting 49, so we know how to undo that. We can add 49 each side. So now all we have left to do is undo a squared. Well, how do you undo something that's squared? We need its inverse operation. And again, we said the inverse of squaring is taking the square root. So we're going to take the square root of each side. Now this is an important part we need to remember. When we take the square root of something squared, that turns into the absolute value. And so remember, the absolute value is measuring the distance from 0. Now, what happens when you take the square root of 49? Well, that's a perfect square factor, a perfect square, so its value is 7. We're not done solving yet because the absolute value is unique, that it's talking about the measuring the distance from 0. So if you think of your number line, you can move 2 directions away from 0. You can go to the left and you can go to the right. So we have to take both of those into consideration when solving. So to show when you go to the left, since you're using negative numbers, we're going to say negative 1 times our starting value here of a equals our distance of 7. And going to the right, that's 1, because your positive numbers, times your starting value of a equals your distance of 7. We have to solve each of these two equations going to the left of 0 and to the right of 0 to find our possible answers. So how do you undo the equation for the left? Well, if you're multiplying by -1, you would divide each side by -1. For the right, if you're multiplying by 1, you would divide by 1. So what would be left with? A can equal -7 or A can equal +7. Both of those are solutions to our quadratic equation. Again, your solutions we talked about were your x-intercepts for your graphs. And so again, we would have one x-intercept at -7, 0, and one x-intercept at 7, 0. Well, what about this equation? P squared plus 12 equals 12. Again, we can see that we're adding 12, so how do we undo that? We would subtract 12 from each side. So now we have p squared equals 0. Again, we're trying to solve for the variable for p, so how do you undo something that's squared? We use its inverse operation. We take the square root of each side. So remember, this turns into the absolute value on the left-hand side, and what happens when you take the square root of 0? That's a distance of 0. So we have the absolute value of p equals 0. Now again, it's measuring the distance from 0, so we still have to talk about going to the left and right. So going to the left of 0 to the right of 0, just like we did before in our previous equation. And if we undid each of these, notice how p equals 0 twice. Again, quadratics have two x-intercepts. Sometimes they're called zeros because the outputs are zeros. Sometimes they're called the roots because those are the building blocks of your equations. So we have two values of 0. Well, what does that mean? If you think about graphically, remember when that happened, we refer to that as a double root because it was intersecting the x-axis at that turning point, the vertex, which is being used on the decreasing and increasing interval. So you could solve a quadratic equation and get two of the same results because it's happening like this, where your turning point, your vertex, is touching the x-axis. And again, you're using both of the decreasing and increasing intervals to create your x-intercepts, your roots, your zeros for the functions. Well, how about this equation? How can we solve for c? Well, right now c is squared, so how do you undo that? You would take the square root of each side. So again, taking the square root of something squared, that turns into the absolute value. And notice how we have the square root of -25. This is similar to what we were working on our previous lessons. Can we simplify this radical? And we know we can rewrite it as the square root of 25 times the square root of -1. And by doing so, since we have that positive number underneath the radical, again, you say, is that a perfect square? Does it have any perfect square factors? So I can simplify like I have in the past. And 25 is a perfect square. So if the area of the square was 25, its side length is 5. So right here, this is going to be 5. We also know when we have the square root of -1 in mathematics, that's now denoted by I. So the absolute value of c is equal to 5i. But again, this is measuring the distance from 0, and you can go to the left and right of 0. For us, since it's an imaginary number, we're going on that imaginary plane, so kind of above your real number of 0 and below. So to show those two, we set up the equations just like we did before. -1 times that starting value of c equals that distance of 5i. And 1 times your starting value of c equals your distance of 5i. You undo each equation like you normally do. So on the left, you're dividing by -1. On the right, you're dividing by 1. And you have your two values for c, -5i and 5i. Well, how about this equation? We've got x squared minus 8x equals 20. This is a little bit different than our previous ones because it wasn't one variable squared and then you had an operation equals a number. Here we've got our x squared, we've got an x, and then we have a constant. But this is looking similar to things that we've done in the past. Notice how all the other equations we got them to undo, or if we're talking about finding their solutions, that's where the output is 0 graphically. So if we make an output of 0 here by subtracting 20, look at what happens to your equation. We've got x squared minus 8x minus 20 equals 0. The left-hand side should look very familiar. We spent a lot of time working with our quadratic expressions, seeing if we could factor them, because if we could factor them, then we knew where the x-intercepts were for our graphs, right? And those x-intercepts, the x values, represented the solutions we just saw for our function. So can we factor x squared minus 8x minus 20? So we're going to think about that leading coefficient here of 1 times negative 20, because there's no greatest common factors to take care of. So we think of two numbers to multiply together to get negative 20, but add to get negative 6. I'm sorry, not negative 6, negative 8. I misspoke. Two numbers to multiply together to get negative 20 and add to get negative 8. And we do know that if we use a 10 and a 2 with a combination of a positive or negative, we can make both of those work. If we have a negative 10 and a positive 2, that meets both requirements. So we could rewrite it if we wanted with our 4 terms, breaking it into pairs and dividing out what they have in common to factor it. Some of you already can put it into factored form, which is fine. I'll just review again how we break it into pairs. So we're focusing on x squared minus 10x. They have an x we can divide out. And the right-hand pair, 2x minus 20, they have a 2 that we could divide out. So if you notice, they both are being multiplied by x minus 10. So one factor is x minus 10, the other is x plus 2. And remember, if both of these are being held together by multiplication and you end up with an answer of 0, one of those items would have to be 0. So we set x minus 10 equal to 0 and x plus 2 equals 0. It should look reminiscent to what we were doing before when we had the x-intercepts and we were trying to write the equation in factored form. Now we just solve each equation. So if it's x minus 10, you use the inverse operation of addition. So x equals 10. X plus 2, use the inverse operation of subtraction, and you get x equals negative 2. These are the two answers to our quadratic equation. So notice how we keep going back to prior methods and using those to help us solve algebraically when we had those features graphically, and we saw how those played out with your functions. So here we have a squared minus 3 equals negative 4. Could we solve this algebraically? And again, we can see that we're subtracting 3 from a squared, so we could undo this equation by using that inverse operation, by adding 3 to each side. So in doing so, now we've got a squared equals negative 1. So how do we undo something that's squared? Well, we take the square root. And remember, we know that taking the square root of something squared, those inverse operations, turns it into the absolute value. And on the right-hand side here, we've got the square root of negative 1, which we should recognize is the value of I. Now again, absolute value means measuring the distance from 0, so we're going to have to set it up like we've done before to find our two solutions for the left and to the right. So again, you've got your negative 1 times a equals I and 1 times a equals I. Undo each equation, so we're going to divide by negative 1, divide by 1, and see how you get your negative I and positive I for your solutions. Now we have the equation 3n squared equals 16n plus 35. I can't undo this equation like we did the last one because we see we've got the n squared and the n. So could we make this equation equal to 0 to see if maybe we could use our factoring approach that we did previously in our lesson? So in doing so, we'd have to subtract the 16n, we can subtract the 35 to put the 0 on the right-hand side. If you choose to put the 0 on the left-hand side, you can use the same approach as well. Because the leading coefficient's not 1, again, you always look to see is there a greatest common factor we can divide out from every single term to simplify the polynomial that you're working with. In this case, 3, 16, and 35 do not have a common factor other than 1. And not all the terms have an n. So we're going to have to take that leading coefficient of 3 times our constant of negative 35 and say, well, are there two numbers we can multiply together to give us a negative 105 and add together to give us a negative 16? And there is a number combination. We could use a negative 21 and a positive 5 to meet both of those requirements. So again, we're using those two to rewrite the middle term. So we have 4 terms to our polynomial now, which lends itself nicely to factoring by grouping. So we look at the pair at the left. Is there a common factor? Well, we could divide out a 3 and an n. And the pair on the right, is there a common factor here? Yes, we could divide out a 5. Notice how each pair was being multiplied by n minus 7. So one factor is n minus 7. The other factor will be 3n plus 5. So this is in our factored form. Now, to solve, we take each factor and set it equal to 0. So if we have n minus 7 equals 0, we can solve this equation by adding 7 to each side. The one on the right, again, trying to solve for n, we would have to subtract 5 and then divide by 3. So our two solutions would be 7 and negative 5/3. I would leave it as negative 5/3 because it's a repeating decimal. It's just easier to leave it things in simplified fraction format when you're solving for right now versus taking the extra step and using your calculator to find an equivalent. Here we have 3x squared minus 11 equals 7. And notice how we only have one variable in the equation, so this lends itself nicely to undoing. We could undo the subtraction of 11 by adding 11 to each side. Then we can undo the multiplication of 3 by dividing by 3. Now to undo something that's squared, we could take the square root. Remember, taking the square root of something squared turns it into the absolute value, and 6 does not have any perfect square factors, nor is it a perfect square, so we're going to leave it as the square root of 6. Again, we do have to take into consideration that we're measuring to the left and right of 0, or think of it as either side of 0. So we're going to set up our two equations to show that and undo each. That means dividing by -1, dividing by 1. So our answers are going to be an opposite of the square root of 6, or think of it as a negative square root of 6, and our positive square root of 6. All right, for this equation, we can see that we have one item squared. So this is similar to what we were doing before when we had a variable like x squared, c squared. We just have something within the parentheses squared. Notice how you also have a fraction. We can think of this also as x minus 4, that quantity squared, being divided by 2, which is equal to 7. So how do you undo division? You would multiply. So to start right off the bat, I would multiply each side of the equation by 2, which means I'll have the quantity of x minus 4 on the left equaling 14 on the right. So how do you undo something that's squared? Well, we take the square root. So on the left-hand side, we'll have the absolute value of x minus 4 is equaling to the square root of 14. Now again, you ask yourself, does 14 have any perfect square factors, or is it a perfect square? If so, you're going to simplify it. If not, you leave it as is. In this case, 14 does not have any perfect square factors, so we're going to leave it as that for our distance, and we are going to solve for both directions from our 0. So again, we're going to divide by -1 on the left, dividing by 1 on the right. And notice here we have one more step to get x alone. We have to undo the subtraction of 4, so we're going to add 4 on each side. So our two results would be 4 minus the square root of 14 and 4 plus the square root of 14. Here we have our equation of 7x squared plus 28x equals 0. Notice that we have some greatest common factors that we could divide out. We could divide a 7 by each term, as well as an x. This is a good one for factoring. So here's our two factors, 7x and x plus 4. If we take each factor and set them equal to 0, that will tell us the values for x for our solutions, the x values for the x-intercepts. So if it's 7 times x, we're going to divide by 7 on the equation by the left to see what we get. X plus 4, use that inverse operation of subtraction to see what you get for x there. And our two answers are 0 and -4. One last equation here, we want to solve for x. So we can see that we've got one item squared, so we're going to start working our way to getting that by itself. So we should subtract 4 first, then divide by 3. And now we have the quantity squared equals 2. How do you undo something that's squared? Well, we take the square root of each side. These are inverse operations. So on the left-hand side, we've got the absolute value of x minus 2 equaling the square root of 2. Again, we're going to go both directions of 0 to find our two solutions and undo the equations accordingly. So the left-hand side, we're going to divide by -1. The right-hand side, we divide by 1. Then we're going to undo that subtraction of 2 and get our two results, 2 minus the square root of 2 and 2 plus the square root of 2.